What is the Heisenberg uncertainty principle?
Heisenberg, together with Max Born and Pascal Jordan, tried a totally different approach using mathematical matrices. As part of their work, Heisenberg developed a principle that demonstrates that in the atomic world our knowledge is limited. The uncertainty principle is written as AX equals h/4n. In words, the uncertainty of a particle's position times the uncertainty in its momentum is never less than Planck's constant divided by 4n. If it has a precise location, then its momentum, and thus its speed, measured at the same time, must be imprecise. Planck's constant is extremely small, and so the uncertainty principle is important only for objects the size of atoms or smaller. The position and momentum of a baseball, for example, can both be precisely known at the same time. The uncertainty principle shows why Bohr's electron orbits cannot exist. If you know the radius of the circle precisely, then it must have some velocity along the radius smearing out its orbit. The uncertainty principle also exists in a form linking energy and time. In this form it says that if an electron is in a state that lasts for only a short time, then its energy is not precisely defined.
What is the latest fusion reactor research project?
The ITER reactor project is international in scope, including the United States, Russia, the European Union, India, Japan, China, and South Korea. The plan is to spend 10 years in construction and 20 years in operation. No electrical energy would be generated. That would require a more advanced reactor, using 0.5 grams of deuterium-tritium fuel. It is designed to produce 500 megawatts of energy over 1000 seconds. For the first time in a fusion reactor, more energy would be produced than needed to run the reactor. In May 2010, contracts were signed to construct the first buildings in the project that are sited in the south of France. Fusion reactions are scheduled to begin in 2018.
How are particles accelerated to very high energies?
The two highest energy particle accelerators are the Tevatron at Fermilab, near Chicago, and the Large Hadron Collider, LHC, at CERN, European Organization for Nuclear Research, near Geneva, Switzerland. Both machines accelerate and store protons moving in circular paths in a metallic tube, called the beam line, from which all but minute amounts of air have been evacuated. Beams of particles circulate through the tube in both the clockwise and counterclockwise direction. The beams intersect at several places around the circle so that the particles can collide head-on. Many superconducting magnets bend the paths of the particles into the circle, while other magnets focus the particles into small beams. Electric fields created in high-power vacuum tubes provide the accelerating forces on the particles. In particle accelerators, energies are measured in electron volts, eV. 1 eV is the energy a particle obtains by being accelerated by a 1-volt potential difference. Modern accelerators give particles energies of hundreds of MeV. Mega electron volts, or GeV, billions of electron volts. The tavotron creates collisions between protons and antiprotons, each giving an energy of almost 1.000 GeV, resulting in an energy of 2 GeV when the two beams collide. In the LHC, both beams are protons. The design energy is 7 GeV in each beam for a total collision energy of 14 GeV.
Are emission and absorption the only ways light interacts with an atom?
In 1917, Albert Einstein proposed a third way light could interact with an atom. If a photon with the correct energy struck an atom in the excited state, then the atom would be stimulated to emit an additional photon and drop to the lower energy level. The two photons leave with the same energy, in terms of a wave, same wavelength, and in phase.
How did probability rather than certainty enter into the model for the atom?
In 1926, the Austrian physicist Erwin Schrödinger, 1887 to 1961, published an equation for a wave function that describes the probability of finding an electron at a particular position. It agrees with Bohr's model in that the most probable radius for an electron is that given by the Bohr model, and the energy of the electron is the same as Bohr calculated. But its results are fundamentally different. The solution of Schrödinger's equation can be shown as a probability cloud that shows the most probable locations for the electron. The n equals 1 state of the hydrogen atom is small and spherical. There are two n equals 2 states. The s state has angular momentum 0 and another spherically symmetric cloud. The p state, with angular momentum 1, has two most probable locations, the top and bottom. The n equals 3 state has three possible angular momenta, 0, 1, and 2. The d state, with angular momentum equals 2, has four angular regions with high probability. Red light is emitted when the electron goes from the n equals 3p state to the n equals 2s state. The lifetime of the higher energy state is very short, less than 1/1000th of a second. So when many atoms emit the light, the energy they emit is spread out. The energy from any particular atom cannot be precisely predicted.
What is active noise cancellation, ANC?
Device that creates a waveform that is the opposite of the noise so that the noise is cancelled.
What is active noise cancellation, ANC?
Device that creates a waveform that is the opposite of the noise so that the noise is cancelled.
What is aerodynamics?
An aspect of fluid dynamics dealing with the movement of air.
What is aerodynamics?
An aspect of fluid dynamics dealing with the movement of air.
What is air drag?
Friction caused by an object moving through air. Drag depends on velocity, area, shape, and the density of the air.
What is air drag?
Friction caused by an object moving through air. Drag depends on velocity, area, shape, and the density of the air.
What is an alloy?
A metal that is a mix of two or more different metals.
What is an alloy?
A metal that is a mix of two or more different metals.
What is an alpha decay?
Type of radioactive decay where nucleus emits an alpha particle. Result is nucleus with atomic number reduced by 2 and mass number reduced by 4.
What is an alpha decay?
Type of radioactive decay where nucleus emits an alpha particle. Result is nucleus with atomic number reduced by 2 and mass number reduced by 4.
What are alpha particles?
Helium atoms with 2 electrons removed emitted with high energy by some radioactive nuclei.
What are alpha particles?
Helium atoms with 2 electrons removed emitted with high energy by some radioactive nuclei.
What is an alternating current, AC?
Polarity of the voltage source and thus current changes back and forth at a regular rate.
What is an alternating current, AC?
Polarity of the voltage source and thus current changes back and forth at a regular rate.
What is an ampere, A?
Unit of measure of electric current. Equal to 1 coulomb of charge passing through a wire divided by 1 second.
What is an ampere, A?
Unit of measure of electric current. Equal to 1 coulomb of charge passing through a wire divided by 1 second.
What is an amplitude?
The distance on a wave from the midpoint to the point of maximum displacement, crest or compression.
What is an amplitude?
The distance on a wave from the midpoint to the point of maximum displacement, crest or compression.
What is amplitude modulation, AM?
M-wave amplitude changes to represent transmitted information.
What is amplitude modulation, AM?
M-wave amplitude changes to represent transmitted information.
What is an aneroid barometer?
Device to measure gas pressure in which the elastic top of an extremely low pressure drum is bent by the pressure.
What is an aneroid barometer?
Device to measure gas pressure in which the elastic top of an extremely low pressure drum is bent by the pressure.
What is angular momentum?
equal to the product of its moment of inertia and its angular velocity.
What is angular momentum?
Equal to the product of its moment of inertia and its angular velocity.
What are the masses of the quarks and leptons?
Because quarks can't be separated, their masses can only be found by using one or more theories to calculate them. The masses of the charged leptons can be measured to high precision. In the standard model, neutrinos are all massless. But recent experimental results demand that they have mass. Masses are given in a unit that is energy divided by the speed of light squared based on Einstein's E equals mc2.
How did a fogged film start a revolution?
In 1896, the French physicist Henri Becquerel, 1852–1908, was exploring the properties of a compound of uranium that glowed in the dark. He placed the compound in a dark drawer on top of a photographic plate that he had wrapped with heavy black paper to make it light-tight. The next morning he was surprised to find that the film was already exposed, or fogged. Becquerel presumed that some unknown rays had been emitted by the uranium compound, gone through the paper, and created the same chemical reaction in the plate that light would. In further experiments he found that a thin piece of metal would block the rays. It was soon alpha, beta, and gammas all are hazardous to our health. Alphas are blocked by skin, but if a radioactive material, such as the gas radium, is inhaled, the alpha particles can cause damage to the lungs. Betas can penetrate skin and tissue and, if they strike a cell, can cause mutations to the DNA. Gammas can cause mutations and kill cells. They are used in cancer radiation therapy.
What is an alloy?
A metal that is a mix of two or more different metals.
What is an aneroid barometer?
Device to measure gas pressure in which the elastic top of an extremely low pressure drum is bent by the pressure.
What are force carriers?
The photon is called the force carrier for the electromagnetic interaction. That means that, for example, the attractive force between two oppositely charged objects is described mathematically not by an electric field, but by an exchange of Invisible, photons. The photon has neither mass nor charge, but does have angular momentum. The gluon carries the color force which, in combination with quarks, creates the strong force. The gluon also has neither mass nor charge. The weak nuclear force is carried by the massive W+, W', and Z degree particles. Gravity is carried by a massless particle called the graviton.
How do the numbers of protons and neutrons in nuclei compare?
For lighter elements, the number of protons and neutrons are approximately equal. For example, the most common isotope of helium with 2 protons is 4He, so it has 4 to 2 equals 2 neutrons. Oxygen, with 8 protons, has 8 neutrons in its most common isotope, 16O. In elements heavier than calcium, 20 protons, 20 neutrons. The number of neutrons is larger than the number of protons. In uranium-238, 92 protons, 146 neutrons, the ratio is almost 3 neutrons for 2 protons.
What is an alpha decay?
Type of radioactive decay where nucleus emits an alpha particle. Result is nucleus with atomic number reduced by 2 and mass number reduced by 4.
Can quarks be free, or are they always bound in the proton or neutron?
There have been many searches for free quarks, but they have never been observed. The theory that describes the interactions between quarks and gluons. Quantum chromodynamics, QCD for short, says that quarks can never break free because the more that the gluons are stretched, the stronger the force they exert. In this way they act like springs whose force also increases the more they are stretched.
What is a half-life? When will a particular radioactive nucleus decay?
It's impossible to know. All that can be known is the average time between formation and decay. And we know that the number of decays will be proportional to the number of nuclei present. Now, suppose we start with a large number of nuclei. In a given time interval, say 1 second, a certain number will decay. At the end of that second, the number of nuclei that haven't decayed will be smaller. So in the next second there will be fewer decays. At some time there will be only half as many decays in a second as there were originally. That time is called the half-life. One half-life later there will be only V4 as many decays as at the beginning. After another half-life there will be half again as many, or 1/8 the number of initial decays.
What is amplitude modulation, AM?
M-wave amplitude changes to represent transmitted information.
Do the masses of the quarks add up to the mass of the proton?
The mass of 2 up quarks and 1 down quark sum to 8.81 MeV/C2, and gluons are massless. But the proton's mass is 938 MeV/C2. How can that be? The remainder of the mass is due to the high energies of the quarks and gluons within the proton.
How was the laser invented?
One of the useful applications of quantum mechanics is in each CD or DVD player in your home, or in the laser pointer. It's the device that uses stimulated emission of light predicted by Einstein so many years ago. In 1953, Charles Townes, 1915, of Columbia University, and later MIT, developed and patented the first application that he called a maser for microwave amplification by stimulated emission of radiation. It used a beam of ammonia molecules and later led to the hydrogen maser, now used as an extremely accurate clock. In 1958, Townes and Arthur Shallow described how molecules could be used to extend the maser concept to optical frequencies. After their paper was published, a number of physicists at university and industrial labs rapidly tried to apply these ideas to working devices. In May 1960, Theodore Maiman, 1927 to 2007, at Hughes Aircraft Company demonstrated an optical maser that used a ruby crystal with a flash lamp. Similar to the camera flash lamp, to put the chromium atoms in the ruby into their excited states. Maiman was involved in a court fight over the validity of his patent for the laser with Gordon Gould. 1920 to 2005, who worked with Townes at Columbia. In 1973, Gould was awarded the patent rights. Maiman won number of awards, but never the Nobel Prize. While the laser was first described as a solution looking for a problem, over the past 50 years lasers have become a multi-million-dollar industry. Lasers have been constructed using gases, as in the familiar helium-neon, or He-Ne laser. The carbon dioxide laser used to cut fabrics and metals, the argon-ion laser used in surgery, the ultraviolet excimer laser used for eye surgery, and the free electron laser used in research. Lasers made of tiny semiconducting crystals are used in CD and DVD players and laser pointers, as well as optical fiber communications equipment that brings video and the internet almost to your front door. Lasers have revolutionized research in physics, chemistry, and biology.
Are there yet more quarks and leptons?
There are two more generations of both quarks and leptons. In the second generation the quarks are called strange and charm. The strange quark was named after particles that contain these quarks. The particles decayed in very different ways and were therefore called strange particles. The charm quark was found in a particle that had a very long, or charmed life. The leptons are the muon and muon neutrino. The muon was first called the mu meson before its true identity was discovered. In the third generation the quarks are called bottom and top. The leptons are called tau and the tau neutrino.
What is the evidence that neutrinos have mass?
The number of neutrinos detected from the Sun is only a fraction of what should be detected if our understanding of the nuclear reactions in the Sun is correct. A proposed solution to this problem is that neutrinos change from one flavor to another on their travel from the Sun to Earth. This phenomenon is called neutrino oscillation. It can only occur if the neutrinos have a small mass. Most experiments that support neutrino oscillation measure the lack of neutrinos of one flavor that they interpret as an oscillation into an undetected flavor. Recently an experiment has detected tau neutrinos in a muon neutrino beam from an accelerator at CERN and a detector 732 kilometers away, in the Gran Sasso tunnel in Italy. This flavor change supports neutrino oscillation.
What is an amplitude?
The distance on a wave from the midpoint to the point of maximum displacement, crest or compression.
What are alpha particles?
Helium atoms with 2 electrons removed emitted with high energy by some radioactive nuclei.
How are neutrinos detected?
Neutrinos hardly interact at all with matter. Some 100 trillion pass through your body every second. Yet the chance that one interacts in your body over your lifetime is only 1 in 4. For this reason neutrino detectors must be huge and can expect to detect only an extremely small fraction of the neutrinos striking them. Most detectors are large cavities filled with extremely pure water or mineral oil. Neutrino interactions result in flashes of light that are seen by sensitive phototubes. The detectors have identified neutrinos from the Sun, from cosmic rays, a supernova, and from reactors and particle detectors. Some experiments have used beams of neutrinos that are aimed through Earth by a reactor or accelerator at a distant detector.
What contributions did Marie and Pierre Curie make?
Marie Sklodowska-Curie, born and raised in Poland, but working in France. Used an electrometer to measure the ionization of the air caused by radioactive minerals. Because the amount of radioactivity produced by a uranium compound depended only on the amount of uranium present, she concluded that the atom itself must be the source. She found that the uranium-containing mineral pitchblende was more radioactive than the uranium itself, and concluded that the mineral must contain a small quantity of another element that was more radioactive than the uranium. Her husband, Pierre, stopped his own work and joined Marie in searching for the element. They started by grinding up 100 grams of pitchblende. But by the time they had found the element, they had processed tons of the mineral. In July 1898 they announced the discovery of an element they named polonium in honor of Poland, where she had been born. In December of the same year they announced they had found an even more radioactive element that they named radium. It took until 1902 for them to separate 1/10 of a gram of radium chloride from a ton of pitchblende. In 1910 Marie announced that she had obtained pure metallic radium. Pierre and Marie shared the 1903 Physics Nobel Prize with Becquerel for their work on radioactivity. Marie won the 1911 Chemistry Nobel Prize for her discovery of polonium and radium. The dangers of radioactivity were unknown when the Curies did their work, but both were affected by it. The radon that was produced when they were processing the pitchblende would have caused lung cancer. But, the leaky windows in their workplace and their frequent bicycle rides in the country spared them. Pierre died in 1906 when he slipped on a wet street and was run over by a horse-drawn wagon. Marie's death in 1934 was due to anemia, known now to be frequently caused by radiation.
What is the origin of the masses of the quarks and leptons?
Peter Higgs, 1929, a British physicist, proposed a mechanism that gives rise to the masses of the quarks, leptons, and the two weak interaction bosons, the W and Z. The mechanism successfully predicted the mass of the Z boson. But it requires the existence of a particle, called the Higgs boson. Despite many searches, the Higgs boson has not yet been discovered. Physicists hope that the Large Hadron Collider, LHC, that started operation in 2010 will accelerate protons to high enough energies that the Higgs will be found.
How does gravity fit into the Standard Model?
It does not fit. Gravity, explained by Einstein's general theory of relativity, is extremely successful on the macroscopic scale. But, all attempts to create a quantum gravity have failed. so have attempts to fit gravity into the standard model.
Do electrons and neutrinos interact with quarks and gluons?
Electrons and neutrinos are called leptons, meaning a lightweight particle. They don't participate in the strong interaction, so they don't interact directly with quarks and gluons. They are, however, involved in the weak interaction through two additional force carrier particles. The W and Z bosons that can interact with quarks. Beta decay involves neutrons, protons, electrons, and neutrinos.
Are protons and neutrons the only particles containing up and down quarks?
In the 1950s, new particles with masses in between those of the electron and the proton were found. They were given the name mesotrons, where meso meant intermediate. This was soon shortened to meson. The most commonly produced meson in particle accelerators is the pi meson or pion. Pions can be positively or negatively charged or unchanged arged. In the quark model, mesons are composed of a quark and an antiquark. It is also possible to create particles with different combinations of 3 up and down quarks. These particles have higher masses than protons and neutrons and can only be created by colliding protons and neutrons together with very high energies. Examples are the combinations UUU with charge +2 and the DDD with charge -1. These particles decay via the strong interaction. The UUU decays when its extra energy creates a pair. The D quark replaces one U quark in the UUU particle, resulting in a proton, and the 5 combines with the extra U quark to form a T+.
How is it explained using quarks?
Beta decay involves 2 steps. First, the down quark changes to an up quark with the emission of a W boson. Then, almost instantaneously, the W changes into an electron and antineutrino. Physicist's diagram. The 2 beta decay processes this way: when a nucleus undergoes beta decay, the number of neutrons goes down by 1. The number of protons goes up by 1, and an electron and antineutrino are emitted. In terms of quarks and leptons, one of the down quarks in the neutron is changed to an up quark in the proton. And a lepton, electron, and antilepton, antineutrino, are emitted. The change from down to up quark is a flavor change, and that can occur only in beta decay. When a positron is emitted in inverse beta decay, an up quark in the proton is changed to a down quark in the neutrino, and a lepton, neutrino, and antilepton, positron, are emitted.
What makes up the nucleus?
Ernest Rutherford, 1871 to 1937, had determined that the charge on the alpha particle, actually the helium nucleus, was 2 proton charges, but its mass was 4 proton masses. Dmitry Mendeleev, 1834 to 1907, in building the periodic table, had arranged the elements in order of their mass and had arbitrarily assigned them sequential numbers that he called the atomic number. The English physicist Henry Moseley, 1887 to 1915, measured the wavelengths of X-rays emitted when metals were struck by other X-rays. He was able to provide a physical basis for the atomic number and, in doing so, greatly strengthened the case for Rutherford's nuclear model. But, as is the case for helium, if the atomic number, and thus the nuclear charge, was about half the atomic mass number, what made up the additional mass of the nucleus? The first proposal was that the missing particle was a combination of a proton and an electron, which would have the correct mass and charge. But the Heisenberg uncertainty principle showed that if an electron were confined to the size of a proton, its energy would be larger than ever observed. In addition, by the late 1920s the angular momentum of the nitrogen nucleus, with charge 7 and mass 14, had been measured. The result could not be obtained from a combination of 14 protons and 7 electrons. In 1931, 2 German physicists found that when energetic alpha particles struck light elements, a very penetrating, neutral radiation was produced. The next year Marie Curie's daughter, Irene Joliot-Curie, 1897 to 1956, and her husband, Frederick, found that if this radiation struck paraffin, protons were ejected, suggesting that the radiation was actually a neutral particle with a mass near that of a proton. The next year James Chadwick, 1891 to 1974, working in Manchester, England, experimentally confirmed the suggestion. The particle was named a neutron, combining neutral with the ending of the word proton. He was awarded the Nobel Prize for his discovery in 1935. The neutron has a mass slightly larger than that of the proton. While neutrons are stable in non-radioactive nuclei, if they are free from the nucleus they decay with a half-life of about 10 minutes. Neutrons are used extensively in creating nuclear reactions and are necessary for nuclear fission, which will be discussed later in this chapter.
How is radioactive decay used to determine dates?
Radioactive carbon-14, 14C, has a half-life of 5,730 years. It is produced in the atmosphere when cosmic ray neutrons strike nitrogen atoms. The 14C then reacts with oxygen to form carbon dioxide in the atmosphere and dissolves into the oceans. Plants take up the atmospheric CO2 in respiration and animals ingest it. Therefore all living things exchange both 12 CO2 and radioactive 14 CO2 throughout their lives. When they die, the exchange stops and the fraction of 14C to 12C in their bodies is fixed. As time goes on, the amount of 14C decreases. Objects up to 50,000 years old can be dated by radioactive carbon as long as correction figures agreed to by international agencies are applied. Willard F. Libby, 1908 to 1980, an American chemist, won the Nobel Prize in Chemistry in 1960 for his development of carbon-14 dating in 1949. There are several other dating techniques that use the half-lives of radioactive isotopes in rocks, including uranium/thorium and rubidium/strontium ratios that extend dating techniques to hundreds of millions of years. Radioactive uranium-235 decays into lead, Pb-207, very gradually. The half-life is 704 million years.
What is aerodynamics?
An aspect of fluid dynamics dealing with the movement of air.
What is angular momentum?
Equal to the product of its moment of inertia and its angular velocity.
What is a laser tweezer?
When a laser is sent through a microscope, it creates a tiny spot of very intense light in the material on the slide. A tiny plastic sphere will interact with the light in such a way that it is pulled into the center of the light. The light can be moved around the slide, dragging the sphere with it. That is the essence of a laser tweezer. The sphere can be chemically attached to the end of a long molecule, such as DNA. When the other end of the DNA is similarly fastened to the surface of the slide, the sphere can be used to stretch the DNA, straightening it out, and measuring properties such as the force needed to stretch it. Proteins, enzymes, and other polymers can be used in place of the DNA, and the forces they exert similarly measured. In addition, the tweezers can be used to sort cells, moving them to specific locations on the slide. We'll explore other mysterious consequences of quantum mechanics in the last chapter. Unanswered questions.
Do all elements have a fixed number of protons and neutrons?
The number of protons in the nucleus of an atom determines what element it is. So the number of protons is fixed. But, the number of neutrons can vary. Nuclei with the same number of protons but different numbers of neutrons are called isotopes. For example, carbon, with 6 protons, can have 5, 6, 7, or 8 neutrons. The isotopes are labeled carbon-11, carbon-12, carbon-13, and carbon-14. A more compact notation is 11C, 12C, 13C, and 14C. Chemical properties in general do not depend on the isotope. There are at least 3,100 isotopes of all the elements presently known.
What is an ampere, A?
Unit of measure of electric current. Equal to 1 coulomb of charge passing through a wire divided by 1 second.
What is active noise cancellation, ANC?
Device that creates a waveform that is the opposite of the noise so that the noise is cancelled.
How were the details of the strong force determined?
Examining the kinds of isotopes that exist gives clues about the nature of the strong force. The most stable nucleus, helium-4, has 2 neutrons having spins in opposite directions and 2 protons also having spins in opposite directions. A majority of non-radioactive isotopes have even numbers of neutrons and even number of protons, allowing them to form pairs with opposite spins. Most of the other isotopes have either an even number of protons and an odd number of neutrons or the opposite. Isotopes with both an odd number of protons and neutrons are extremely rare. So, the strength of the strong force clearly depends on the spins of the nucleons. The mass of a nucleus is less than the sum of the masses of the protons plus the sum of masses of the neutrons. The larger the mass difference, the stronger the forces holding the nucleus together and the more energy needed to pull the nucleus apart. Studies of the mass of the nuclei can thus be used to gain further insight into the strong force. Maria Geppert-Meyer, 1906–1972, was a German-born American physicist who explained why nuclei with certain numbers of protons and / or neutrons, called magic numbers, were extremely stable. Her theory showed that the nuclear force depended on both the spin of the nucleon and its orbital angular momentum. The magic numbers are 2, 8, 20, 28, 50, 82, and 126. Thus helium-4, the most stable nucleus, has a magic number of protons and a magic number of neutrons, and so is called doubly magic. Oxygen 16, calcium 40, and calcium 48, and lead 208, which is the heaviest stable nuclide, are also doubly magic. But, are all nuclei stable? What rays do radioactive materials emit? Among the scientists who explored radioactivity immediately after Becquerel's discovery was Ernst Rutherford, then at McGill University in Montreal, Canada. He and Frederick Soddy found that uranium and thorium emitted 2 different kinds of rays. One could be stopped by paper, the other required metal about a centimeter thick. Rutherford named them alpha and beta rays after the first two letters in the Greek alphabet. In 1907 he named the even more penetrating rays produced by radium gamma rays. In 1900 Pierre, 1859 to 1906, and Marie Curie, 1867 to 1934. Using an electroscope, found that beta rays are negative particles. Becquerel used the same kind of apparatus J. Thomson. 1856 to 1940, had used, see the chapter What is the World Made Of? To measure the ratio of mass to charge of an electron to determine that betas typically travel at about half the speed of light and are identical to electrons. In late 1907 Rutherford demonstrated that alpha rays were helium atoms with the two electrons removed. He had not yet discovered the nucleus. Today we say that an alpha particle is the helium-4 nucleus. Gamma rays were later found to be very high-energy photons.
What is air drag?
Friction caused by an object moving through air. Drag depends on velocity, area, shape, and the density of the air.
What is quantum mechanics?
The field of study of atoms by themselves, as well as in molecules, liquids, and solids in which the wave nature is important is called quantum mechanics. The atoms obey the Schrödinger equation. But for any atom more complicated than hydrogen, the equation can be solved only by a computer. Using computers to solve equations, run complicated models, and simulate experiments is an important subdivision of the study of physics called computational physics, which now has equal status with theoretical and experimental physics. Some of the recent accomplishments of quantum mechanics are in the areas of condensed matter physics, or the study of solids, and atomic physics. All of the integrated circuits used in MP3 players, televisions, cameras, and automobiles are designed using quantum mechanics. They are all based on diodes and transistors, where quantum mechanics describes and explains their properties and guides materials scientists to select appropriate materials for their construction. One of the most exciting new materials is graphene, a film of carbon where the atoms are in hexagon-shaped arrays, but the film is only one atom thick. Graphene is being investigated as a way of constructing extremely tiny transistors, and thus powerful integrated circuits. It may also be used as a sensor to detect single atoms or molecules of selected materials, or as a transparent conductor for touch-screen computer displays. Its discoverers won the 2010 Nobel Prize. From 1924 to 1925, Einstein and the Indian physicist Satyendra Nath Bose 1894 to 1974, predicted that if an atomic gas were cooled enough the atoms could form a new state of matter that would exhibit quantum effects on a macroscopic scale. The first experimental confirmation of this prediction occurred in 1995 when Eric Cornell, 1962, and Carl Wieman, 1952, at the University of Colorado cooled a gas of rubidium atoms to about 1/6 of a millionth of a Kelvin. They and Wolfgang Ketterle, 1957, at MIT shared the 2001 Nobel Prize for their work. While this new state of matter, called a Bose-Einstein condensate, has no existing applications, physicists are using it to improve their knowledge of how atoms interact at very low temperatures and to explore possible future applications to atomic clocks and computers.
What is an alternating current, AC?
Polarity of the voltage source and thus current changes back and forth at a regular rate.
What holds a nucleus together?
Protons, all being charged positively, will repel each other. So there must be an attractive force that holds the nucleus together. The strong nuclear force acts between protons and protons. Protons and neutrons, and neutrons, and neutrons, all with the same strength. Because the strong force acts the same on protons and neutrons, the two particles are frequently lumped together under the name nucleon. While the repulsive electromagnetic force acts over long distances, the strong nuclear force only acts between nucleons that are in contact. Nucleons have angular momentum, or spin, and the strong force depends on the relative orientation of the spins. The force is stronger if the spins are in opposite directions.
What is angular velocity, CO?
Equivalent of velocity for rotational motion.
What is angular velocity, CO?
Equivalent of velocity for rotational motion.
What is an anode?
Positive electrode or terminal on, e.g. a battery, electrolytic cell, or cathode ray tube.
What is an anode?
Positive electrode or terminal on, e.g. a battery, electrolytic cell, or cathode ray tube.
What is an antenna?
Used to transmit or receive electromagnetic radio waves.
What is an antenna?
Used to transmit or receive electromagnetic radio waves.
What is an antinode?
Locations in a standing wave where there is the largest amplitude caused by constructive interference.
What is an antinode?
Locations in a standing wave where there is the largest amplitude caused by constructive interference.
What is an apparent weightlessness?
Occurs when an object is in free fall. Force on object in direction opposite gravity is zero.
What is an apparent weightlessness?
Occurs when an object is in free fall. Force on object in direction opposite gravity is zero.
What is the Archimedes principle?
An object immersed in a fluid will experience a buoyant force equal to the weight of the displaced fluid.
What is the Archimedes principle?
An object immersed in a fluid will experience a buoyant force equal to the weight of the displaced fluid.
What is an arrow of time?
The forward direction of time is the one in which entropy increases or remains the same.
What is an arrow of time?
The forward direction of time is the one in which entropy increases or remains the same.
What is astrophysics?
Study of how astronomical bodies, such as planets, stars, and galaxies, interact with one another.
What is astrophysics?
Study of how astronomical bodies, such as planets, stars, and galaxies, interact with one another.
What is atmospheric physics?
Study of the atmosphere of Earth and other planets, especially effects of global warming and climate change.
What is atmospheric physics?
Study of the atmosphere of Earth and other planets, especially effects of global warming and climate change.
What is atomic and molecular physics?
Study of single atoms and molecules that are made up of these atoms.
What is atomic and molecular physics?
Study of single atoms and molecules that are made up of these atoms.
What is an atomic mass number?
Number of protons and neutrons in nucleus.
What is an atomic mass number?
Number of protons and neutrons in nucleus.
What is an atomic number?
Number of protons in the nucleus and thus the nuclear charge.
What is an atomic number?
Number of protons in the nucleus and thus the nuclear charge.
What is a qubit?
Qubit is short for quantum bit, the basic piece of information for a quantum computer. A qubit can be the state of an atom, ion, photon, or an electron. As was the case of the polarization of the two gammas, the qubit doesn't have a value of 0 or 1, but is in a state that is a superposition of 0 and 1, so it can have any value between those two numbers. If you try to measure the value of the qubit, you will get either 0 or 1. So it will act like a bit in a normal computer. The trick is to use one of two entangled photons, or atoms, to determine the qubit state without collapsing it into either 0 or 1. Quantum computers are by nature parallel machines that can work on many problems at once. At this time computers with 12 qubits have been demonstrated. So there is a long way to go before such a device is practical. Still, progress is being made. A company has demonstrated a way of using the kind of chip lasers used in CD players to create entangled photons, greatly reducing the size, complexity, and cost of a quantum computer.
Could antimatter destroy the Vatican?
In Dan Brown's novel Angels and Demons, physicists at CERN use the LHC, the Large Hadron Collider, to produce 1/4 gram of antimatter. The material was stolen in order to destroy the Vatican. It is true that if 1/4 gram of antimatter were to completely annihilate with 1/4 gram of matter, the amount of energy produced would equal that of the bomb that destroyed Hiroshima. But, in over 10 years of experimental production, only 10 million antiprotons have been trapped and stored for times ranging from seconds to months. 1/4 gram is 1016 times as many antiprotons. Further, the antiprotons must be stored in extremely cold. Totally, antiprotons are created in accelerators, where the accelerated particle is slammed into a metal target, emitting gammas that create, in this case, proton-antiproton pairs.
What is angular velocity, CO?
Equivalent of velocity for rotational motion.
What is an atomic mass number?
Number of protons and neutrons in nucleus.
What will happen to the ever-expanding universe?
If the acceleration of the universe continues in many billion years, galaxies beyond the Milky Way and its companions will become invisible because their apparent velocity as seen from Earth would exceed the speed of light. In some models, dark energy would rip apart all galaxies and solar systems, and eventually become so strong that it could tear apart atoms and even nuclei. The universe would end in what has been called the Big Rip. In other models, gravity would again take over, causing the universe to contract and end in the Big Crunch. More measurements of acceleration are needed to decide between these two ultimate ends.
What is atomic and molecular physics?
Study of single atoms and molecules that are made up of these atoms.
What is entanglement?
Consider what happens when a positron and electron annihilate. Two gammas, high-energy photons, are produced that go off in opposite directions, 180 degrees apart. They can be detected many meters from their source and have opposite spins. But which gamma has which spin is a random choice. That is, for each gamma there is a 50/50th chance that it will be in a particular direction. Suppose you find that the spin of one gamma is pointing up. But, the moment you detect the spin of that gamma, the spin of the other gamma must be pointing down. The result of one measurement determines the results of the other. The two detectors would measure the spins of their gammas at the same time. So there is no way that one gamma could communicate with the other gamma. Physicists say that the spins of the two photons are entangled and that the spin state of each photon is the superposition of the two possible spin directions. When the spin is measured, the wave function collapses and gives a definitive result. Albert Einstein, 1879 to 1955, called results like this spooky action at a distance. Others have called it quantum weirdness. Similar results can be obtained with atoms or ions, in which case the photons are light quanta and may be transported through space, or the air, or by optical fibers. For example, if an atom is excited by the absorption of a photon, it can emit two photons that are entangled the same way the gammas are in the example above.